And of course, I want to welcome you to new month. Today, the focus is going to be on some practical examples. You know, the essence of why we are trying to learn what I call statistical theory is to enable the student and the world in general to understand how we put in place, some statistical techniques, models that we use, in the real world. Let me say this. The existence of reality is independent of human knowledge. And, we live in a world where there's a lot of variations, right? Different things happens in different days. And because of that, we got worry. And as human being, we want to secure our environment. Securing our environment is actually we want to understand our environment. We want to understand our political environment. We want to understand our medical environment, sociological environment, economic environment, and so on, like that. Understanding of environment requires that we should have a knowledge. Where will the knowledge come from? The knowledge is going to come from the information we got at a particular point in time. So knowledge to understand our environment come from information. Where will the information come from? Information is going to come from data. Okay? Now, but let me tell you this. When you collect data, we don't get information immediately. Information is not readily available. There's something need to be done to data. And what needs to be done to data is to use an appropriate statistical model on data. And how are we going to know which statistical model is appropriate? And that is the essence of learning statistical theory. So all what we've been doing is just to understand, how we derive some estimator, some techniques, approaches that work in case we collect data, okay, how we can actually get the information that we need from the data. Of course, the parameter of interest, the information that I talk about you could be seeking information about the mean, okay, maybe the average, you're trying to figure out what is the average annual household income in a particular country. It could be proportion. Maybe you actually want to figure out the proportion of, the citizen of a particular country that approve the job the president is doing. It could be maybe you want to figure out how the difference of means in two different populations, you could be difference of proportion in two different populations. And not only that, at times, you could be seeking information about what is the true relationship between variables. And that was why, in any of that, we need an estimator because we are not going to be working on the entire population. We're actually going to take a sample. Of course, we need to have a suggestion about what estimator that actually work. And you know what I told you the other time, we actually get some basic properties of estimator, like unbiasedness. I've walked you through that. Efficiency, I've walked you through that. Consistency, I've walked you through that. Sufficiency as well. And of course, we were dealing with a linear model, situation where we are seeking to get the true relationship between variables. Of course, we actually come across an idea that put into consideration minimizing the sum of square error. And of course, we derive least square estimators. And I remember we also investigate the properties of the least square estimator, which we investigate the unbiasedness property. We realize that the beta not curve, the beta one curve, they are actually unbiased. We also investigate the consistency of that when the sample size increases, the limit of the sample size tending toward to infinity. Of course, we know the variance converge to zero. We've done all of that. Now, after doing all of that, what is the next thing to do? Of course, we've actually embarked on a journey of theoretical statistics, and we've been able to come across some estimator that work. And right now, we want to go into applied statistics where we're going to apply, those techniques. And that is why I'm actually calling this some practical examples. Let me tell you, if you're doing applied statistics and you don't ask what is behind the scene, you don't care about the appropriateness of your technique, you could mislead the world. And that was why, we actually need to, we shouldn't handle theory or statistics with levity. Okay, we need to be able to understand how some method works. Now, I want to walk us through this real life of practical situation. In many real world, situations, the most appropriate deterministic component of a model is non-linear. You remember what we've been doing? We've been talking about linear relationship. It is not all the time that the relationship is actually going to be a straight line. Okay, if you want to go from economics to biological phenomena, most of the time, what we normally have is a non-linear relationship. For instance, if I want to talk about relationship between environmental performance, okay, a relationship between and the foreign direct investment, environmental performance and the foreign direct investment. Okay, economics is going to tell you the relationship is not going to be a straight line. Now, and I also want to cite a biological example we could have. For instance, if I'm talking about population of plants, okay, or animals, okay, that tend to grow exponentially, exponentially, not arithmetically. So when something grows exponentially, you don't assume a linear relationship. So if you denote YT, okay, to be the size of the population at time T, okay, and we might employ this model. If you take a look at this model right now, this model specification here does not appears to be a linear one. This is a non-linear one. The one we'll be doing is linear one. But let me tell you this. We're talking, even though we know that in most of the real life situation, relationship used to be non-linear, but I want to tell you the idea of linear can still be used. Because of that, I'm actually going to say, we got two types of non-linear model. Okay. The first one is going to be called intrinsically linear, intrinsically non-linear. And we have, this is the situation. What actually happened is this. Well, we have a non-linear model that can be linearized. I'm going to say that again. If actually it's a non-linear model, but it can be linearized when you use certain mathematical transformation. Then we're actually going to call that non-linear, okay, intrinsically, linear. You get what I mean? So because initially it was a non-linear, but at the end of the day, when we linearize that, it's actually linearized. And we also have some non-linear model that cannot be linearized. If they cannot be linearized, we also have another approach. We can borrow an idea from mathematics, where we're going to use what I call numerical approach, where the idea of algorithm will be used. But right now, today, I'm actually want to focus on a non-linear model that can be linearized. When it is linearized, we can apply linear approach. Now, when you take a look at this guy now, let us, you are relating the population at time t, okay, to time, right? Time t there is actually the independent variable. Now, this is not linear, but let us take the log of both sides. Taking the logarithm is a transformation. At the end of the day, we're going to get this. Any question? The logarithm of that. That will be, the logarithm, like talking about the natural log right now. So which is this going to be like, you can see what we have right now. It means the response variable, the dependent variable is being logged. The intercept is being logged. And of course, the error, we added error. Okay, so we take a look at this guy now. We can use the idea of linear model, even though it's a non-linear model, but after taking a logarithmic transformation, it becomes linear. Now, when you take a look at this now, if you collect your data now, take a look at this. You are collecting the data population at a particular time. That's what it means. Okay. Now, we now want to use the method of, least square. The same way, we did the other time. The other time, when we're working on a linear, right? Okay, we actually minimize sum of squared. We differentiated with respect to beta naught and beta 1. We're able to put in place the estimator for beta naught and beta 1. But do you know that if you take a look at this now, because we have a new parameters after the transformation, take a look at what I have here, ln alpha naught and that. So what I'm going to do now, if you take a look at this guy here, okay, you're actually going to see that beta naught is being replaced by log of alpha naught. And you're actually going to see that time replace x, because we're telling the world the independent variable is actually x. And not only that, take a look at this too. Instead of us to be working with yt, we're going to be working with the log. But let me tell you this, if I now want to equate this to this, what I'm telling the world, take a look at this y. Y that is having something, it means I have, that's a transform y, which is the same thing as this guy here, which is the same thing as this guy here. Okay, so take a look at that. Now, when you now compare, you're actually going to see that we got a new y, a transform y, and our independent variable s is time t. Then our beta naught, if I want to go by the beta naught that I have in the original model, is actually going to be equal to the log of the alpha naught. And of course, the beta 1 is still the same thing as alpha 1. Now here we're actually using the idea of a linear model for non-linear model that can be transformed. Any question on this? Before moving forward, any question? Any question? Now the next thing we're going to do now. You remember the other time we derived an estimator for both beta naught and beta 1. Okay, beta 1 cap, beta naught cap. We now want to use this idea for, for the non-linear. After transformation, we already know that this is going to be equal to that. And don't forget, if you come back here, if beta naught equal to ln of alpha naught, what is alpha naught? Alpha naught is going to be exponential raised to power beta naught mathematically. Take a look at that. And that was why here we say alpha naught is going to be exponential raised to power beta naught. Alpha 1 cap remains as the beta 1 cap. If you compare the two now, you're actually going to see that if you compare this guy with this guy, wherever you see x, it will be replaced by time t. time t is an independent variable. And of course, the log of yt will replace yt. And that is what you can see. And when you take a look at here now, when you take a look at this guy now, okay, what is my beta naught cap? The beta naught cap is actually this. You remember the other time, the beta naught cap is y bar minus beta 1 cap x bar. So what is happening now? The lane of yt is replacing yt, and t bar is replacing x bar. Take a look at that. So which means if I have a specification that look like a specification, it'll actually look like this. After transformation, it's going to look like this. And I will be able to use a approach of linear, okay? Can use a linear approach, okay, on that, okay? I can see some student online. I need someone to confirm if you're hearing me clearly. There's a few online. Okay, I also need another person to talk. I can see I just want to hear you, if you can, but there's a few online.
I can hear you.
Okay, thank you for that. Okay, now the next thing that I want to talk about now is, can we work with real life data on this? Okay, because of that, we want to work on the real life example. But if you take a look at what we've done here, based on this specification, it is only the dependent variable that has the log. After the transformation, right? After the transformation, the dependent variable y has a log, but the independent variable t does not have a log. Does that make sense? Based on that specification, we could have another specification where two of them is going to have a log. Does that make sense? And I'm going to walk you through such example. We are both dependent and the independent variable, they're going to have a log. Let's take a look at weight and the length of animal. And the specification is this. If you take a look at this specification, it's different from the other specification. Here they are trying to tell you the average weight of animal, okay, is not linearly related to the length. If I see a crocodile is an animal, okay, they are trying to say, based on the length of a crocodile, can we have a prediction of the weight? Of course, you know, in agricultural market or in fishery or aquatic market, the weight is as economy value, right? The more weight, the animal. Does that make sense? Okay, now, this specification was actually put forward by mathematicians that look, they look at the relationship between the weight of the animal and the length, and they come out with that specification. This specification is actually a nonlinear. Now, if we want to see whether this can be linearized, we're going to take the logarithm of both sides. Taking the logarithm of both sides and adding error, we have that guy. Can you see that? In this transform module now, you're actually going to see that both the dependent and the independent variable, they actually have log, right? This is a log, the log of the response and the log of, the independent variable. Now we've been able to achieve linearity now, even though initially it was not linear in nature. Okay, I told you when you have a non-linear specification, non-linear in variable, Okay, you have got a nonlinear invariable. This is nonlinear invariable. You know, a nonlinear invariable can be linearized. But when you have a nonlinear parameter, a nonlinear parameter is the one that cannot be linearized, that we're actually going to call intrinsically nonlinear, because they cannot be linearized. Whatever transformation technique you use on them, they cannot be linearized. And if they cannot be linearized, we can only seek redress using algorithm, resulting into what I call numerical approach in mathematics, that we call like method of first position, Newton-Raphson method, and stuff like that. But the one we're dealing with here is intrinsically linear. A non-linear is intrinsically linear. Intrinsically linear means a non-linear that has been linearized. Like here now, this has been linearized. And of course, we can actually equate that to our, the original model. Now, if you want to compare this now, you're going to say your beta naught is log of alpha naught. You're going to say your beta one here is still alpha 1, but your x is log of the length. Does that make sense? So take a look at that. So that's why take a look at that. So that I'm doing here, s equal to this, the beta not equal to that, and that equal to that, which means after you have succeeded in linearizing, okay, after you have succeeded in linearizing, you're now going to compare your new model with the original model that you've learned. Okay, those of you live, anybody want to talk, like ask question, you can first chat with me or indicate by giving me a thumbs up you want to ask question, then I'm actually going to allow you to talk. Okay, thank you. Now, we want to go into an example. Take a look at the data. This is the data. We have a data set on weight and the length of animal, but you know what? Because of the model, because of the transform model, we decided to find the log of the dependent variable y and also find the log of the independent. So which means when you take a look at this data set now, how many alligators are we using? 15 alligators. Okay. Biologists have helped us to collect data set on the length and the weight of alligator. And the result, the value that you are seeing here is not the original length. This is not the original weight. What we have right now is the log of the length and the log of the weight. Why am I taking the log of the two? Because when I see the specification, okay, of the model, okay, this is the specification of the model, and after taking the log of both sides, I arrive at this, and that gives me the sense that, okay, in my data, I'm actually going to take the log of the weight and the log of the length. We don't just do what we do. There's a reason why we do what we do. Does that make sense? So right now, so what you're seeing in the data now, okay, so this particular data set, was actually collected in Florida. There was a time I was watching TV and, crocodile was walking on the streets in the state of Florida. Okay, so, and also, this denotes, okay, weight in pound and the length in inches for 15 alligator captured in Central Florida. Okay, they captured in Central Florida. And let me tell you this, after the specific, which means in exam, I can just give you this. I'm just going to give you 1 second. I'm going to give you data, and I'm just going to give you this relationship. Take a look at that. You are going to be the one that will first introduce the log to the both side, and you're going to arrive at this guy. When you arrive at this guy, you'll be able to compare with the linear model you've learned, so that you'll be able to know what are you going to do with x, what are you going to do with y. You're going to log the x, you're going to log the y. Okay, now, but let me tell you this. You're so lucky. The data set given here, they've already helped you out. They've helped you to take the log of the data. You can see x equal to the log of the length and y equal to the log of the weight. So which means okay, somebody want to ask question. Give me 1 second. I'm actually gonna allow. Now, can you talk now? Let me see if I can hear you. The person that want to ask us.
Yeah, can you hear me?
Go ahead.
Can you hear me?
I can hear you. Go ahead.
Okay. Yeah, I was just wondering why T like transforms to X specifically. Like, is this just an arbitrary thing that you're choosing? Like, could you say X is technically like
Okay,
X?
give me 1 second. I want to hear you clearly.
Okay.
Now, go ahead.
Yeah, I was just wondering why T transforms to X specifically. Like, is this just an arbitrary thing, or does it have to do something with independence?
Okay, you asked why is it that x is a log of n, right?
No, T. Why does T like the length or of time always transform to X?
Oh, okay. Thank you so much. Why is it that t always transform into x? Is that what you mean?
Yeah.
Okay, because when you are talking about uh, okay, we want to believe changes when time changes, right? So time is going to be an independent variable. If I want to know the population, that's why we normally say population at time t. So in that situation now, the population is going to be the dependent variable. Time is going to be independent. So which means we're trying to say population depends on the time. Does that make sense to you now?
Yes, that does. I
Have
think.
I answered your question?
Yeah, I think so. I think I was just like wondering, um, n- yeah, I think so. Okay, we'll just go with that.
Okay, so what I was trying to say is this. You asked why is it? I think in your question you actually referring to. Let me take you back. You are actually referring to here. Okay. Now, if you take a look at here, we said, for example, many population of plant or animal tend to grow at an exponential rate. When a population is growing according to time, which means what determine the population, one of the major factor of the population is time. And that is why time is going to be independent variable. And that is why the specification here is actually relating the population with time, except that the relationship here is non-linear. I don't know whether you guys have heard about what I call, there's something that in economics that they call, there's a Matthias population theory that's going to tell you why population increase in geometric progression, food increase in arithmetic progression. And because of that, we believe between population and time, the relationship is multiplicative, not arithmetic. So I don't know if I've answered your question now.
Yeah, I understand that part. So then our alpha,
Is that
like
what?
the param, I understand that part. So then our is alpha always, or like we can't assume independence because we don't know the underlying distribution, or well, we know it's exponential, but we like I'm confused about that part. Are those also independent variables?
Okay. This is this is what happened. I understand your question now. Okay, take a look at this guy. Do you see what I circled, right?
Yeah.
Okay. Now, if you see the way it is specified, this is telling you here that they are looking at the dependent variable y that
Yeah.
depends on time. Do you see subscript T, right?
Yes.
And that is why in the specification here, we are actually seeing T, right? You see
Yeah.
time, right? So that is the reason. So now
if you now want to know, you know, the moment you have this guy here, the very first thing that will come to mind is this is a non-linear specification. All what I need to do is to take the log of both sides. The log of both sides is going to give me this. When I take the log of both sides, look at what I'm having now. This is giving me a sense of, you know, trying, if I equate this to what we normally have, you know, what you learn in this class is beta naught plus beta 1 x, right? Beta 1 x plus the error, right? That's what you learn in this class. Now, now you're going to compare, now you're going to say, and you know, here we normally say y, right? Equal to that. So it means here now, instead of y, we're going to have the log of y. Instead of beta naught, it's going to be log of alpha naught. Instead of beta 1, it's still going to be alpha 1. And our x is automatically t. Have I answered your question now?
Yeah, that makes a lot more sense.
Okay, thank you so
Thank
much.
you.
Want to reset that.
Okay, now we are already working with the data. Okay, like I said, you need to pay attention to the original equation given. If you look at the specification here, we're not talking about time anymore. This is relating the weight of animal with the length. That's why you don't see time. At times, we may be referring to growth. If you're talking about growth, time has to be involved in growth. But right now, the relationship is actually on weight and the length. When I know the length of an animal, can I determine the weight? This specification that you see here, okay, has been given by mathematicians. They've looked at the relationship between weight and the height, and they realize that on average, weight can be related, you know, to the length, but it's going to have a this is a non-linear specification. Moving forward, you need to take the log of the both sides because it's a non-linear. The essence of taking the log of the both sides is to linearize. Why do you want to linearize? So that you will be able to use a linear technique. That is the essence. And after linearizing that actually give you this. When you take the log of both sides, you now equate that to the linear model you've learned. Equating that to the, don't forget in your new model here, you are no longer talking about alpha naught. I mean, you are no longer talking about beta naught and beta 1 you learned before. You're talking about alpha naught and the alpha 1. But if you relate that, if you want to use that approach, if you have obtained your beta naught, then in the model, it's going to be log of alpha naught. If you have obtained your beta 1, okay, so in the model, it's actually going to be that. Okay. Now, if you take a look at this now, like I said, based on the specification, based on this guy, we take the logarithm of that, we arrive at this, equating this to the model we have. We now know that our x is that. That was why we said in the length, we have to take the log of the length. The log of the length is going to give us x that we know. And, you know, here, you see that? If you compare, and if I want to get y that we're going to use is going to be the log of the weight. And you know what? In this particular data, take a look at that. The values that you see here, they are not the original length of the alligator. These are the values that we got after taking the natural log of those values. Does that make sense? Which now becomes our X. The values here are not the original weight of this alligator. We got this value after taking the log of the weight. Now, if you have X and Y, we can use the linear model that we have learned. Take a look at this. You know, this is a model. Now, in a linear model, you know, we need to get what is the beta naught, what is the beta 1, right? Now, if you come here, the beta 1 cap is xxy over xxx. Y, the beta naught cap is y bar minus beta 1 cap x bar. Now, how am I going to get xxy? How am I going to get xxx? Now you come here now. Okay. If I want to get, take a look at this. Take a look at what I've done here. xxy, I need summation xy. Where is that going to come from? You know, in the table I have x and y, you create another column that is going to be xy, right? Do you understand? And you need the total. You know, you're just multiplying this by that, and you get all of that here. Then the sum of the products. And that is going to give you this guy. That is going to give you this, which is this guy. Now, you need the sum of x and the sum of y. What is the sum of x? What is the sum of y? As it appears here, what is the sum of this guy? That will be the sum of x. What is the sum of this guy? That will be the sum of y. So when you put that here now, I'm trying to tell the world the sum of x is this guy. The sum of y is this guy. What is the 15? Of course, n, which is the numbers of alligator in the data. Now, when I do all of that, I got this. This is x, xy. Then I want to get SSX. You remember the other time? I told you x, SSX is summation x minus x bar all squared. When I expand this, is the same as this, which is the same thing as summation s squared minus 1 over n summation s all squared. How am I going to get summation s squared? If you take a look at this guy here, of course, this is easy to get. When you have the sum of s, you square the value. But what about this guy? You need to come back here. Okay, you need to get another column that is going to be what? S squared. Okay, this guy is squared, that guy is squared, until you get to this guy is squared. Then all what you got to do is to add them up. Does that make sense? That'll be some S squared. So when you do that, you actually gonna get, that's what we're doing here. Take a look at that. You can confirm that. We got is 0.8548. Lastly, you need SSYY. Okay, the XYY is going to be that for summation y squared out. Then you got that. Now, what is your B1? What is your beta 1 cap? Look at beta 1 cap. SXY over XSS. What is your beta naught cap? Y bar, because y bar is going to be summation y divided by n. Beta 1 cap. Now, see, you know the other time we proved that this guy and this guy, they are connected. Because the covariance is not equal to 0 when they are related. The only condition under which they are not going to relate is when X bar is 0. So right now, if you want to get the right value for beta naught cap, you can see your beta 1 cap has to be correct. You know, we find the beta 1 cap that we got here is what we are substituting. You see that? Then finally, what has happened here? We've gotten the beta 1 cap and the beta naught cap. Okay, we've gotten the beta naught cap and the beta 1 cap. But let me tell you this. What do they ask us from the question? What we need in the specification. Take a look at what we need in the specification. The parameters in the specification is alpha naught and alpha 1. It is not beta naught and beta 1. Does that make sense? Now, because at the end of the day, this is the way we're going to write. All what they are asking for us is what is the value of alpha naught, what is the value of alpha 1. Now that I got my beta naught and beta 1, and I know, take a look at this. This guy is the same thing as this guy. If I want to, and I have my beta naught now, if I want to get alpha naught, okay, I'm going to exponentiate beta. I'm going to exponentiate that. And if you take a look at this, we're told that alpha 1 is the same as beta 1. If you want to, so now, if you come back here now, you know, we said, based on what we see the other time, say alpha 1 equal to that. But if we want to get alpha naught, we need to exponentiate beta naught. Why are we exponentiating beta naught? Because this is how I know. After simplifying, give me 1 second. Okay. After performing logarithmic transformation, this is what we have. And we know that our beta naught, okay, is actually equal to that. Let's take a look at this. And mathematically speaking, if I know beta naught and I want to find alpha naught, if beta naught equal to the natural log of alpha naught, then the alpha naught is going to be exponentiating beta naught. And that was why we were exponentiating. Beta naught. And finally, we got, this is our alpha naught. And our beta 1 is the same as the alpha 1. And we're now going to go back to the original model before transformation. We're going to go back to the original model. The original model before transformation is this guy. When you get to the original model, you're going to put a cap on the weight, because don't forget, you are estimating the weight. You're going to put a cap on the alpha naught and the alpha 1, even though in the specification, there was no cap on them. Because in the specification, they are parameters. Does that make sense? No cap on them. So right now, you're now going to go back, you know, and rewrite that. So take a look at this. What has happened? I've already replaced alpha naught cap that I got to be that, and the beta and alpha 1 cap that I got to be that. So what are we trying to say? We're trying to say, if I know the values of a weight, of a length, it may be given any alligator in Central Florida. Okay, if I know the length of the alligator, I can use this model to predict what the weight is going to be. Okay, and that was why in many cases, alpha 1 will be close to 3. You can see what is the alpha 1 here is 3.4312, because weight of volume is roughly proportional to the cube of the linear measurement. This is a theory that has been verified by biologists, a mathematician, you know, those who are actually applied maths into biological situation, they've already seen it. And look at what we have in the data now. Actually giving us the alpha 1 here is very close to 3. Is there any question on this? So like I said, those of you online, if you want to ask question, you actually going to indicate by reaction, or you send me a message and I'm going to allow you to ask question. Okay, take a look at this. Can I say something? The probability of this coming, something like this coming out in the final is 1. So it's 1. So you're gonna make sure you practice that. Okay. Now, what we've done today is, trying to see how, things work in practical situation. I told you the other time, whatever we learn, okay, we're actually going to apply it in the larger society. All this why we'll be talking about theoretical statistics, how modules are formulated, which particular module that work. We are actually doing that just for us to know what happened behind the scene in case things are changing in life. We're actually going to have a way to change the module. Because we want a situation whereby there's going to be an agreement between module we use and reality. If there's a disagreement between our module and reality, the deviation is going to be much. The distance is going to be much. What distance am I talking about? Error. I told you there's going to be error. There's going to be a gap. But when you are using an appropriate module for a given situation, the gap is going to be very, very small. I mean, the error, you would have controlled the error using an appropriate model. And that is why, most of the time in statistics, assumption revolve around the error. If I want to know how good is a model, of course, what I actually need to do is to investigate whether assumption hold. Assumption revolve around the error. So, finally, like I said, I have a talk coming up in December 6th. I'm going to give a seminar on behalf of School of Statistics, which I also enjoin, I encourage you to, I think what I'm going to do on that day of my lecture, of that day of my seminar, for this class, then there's not going to be lecture. I'm going to send a message, I want to encourage you to, to attend. Okay, somebody said, can you send out detail for your seminar? Of course, I will do that. Okay, I'm actually going to do that. Send, the seminar is going to be super because I'm going to, use the knowledge of theoretical statistics on how we can actually test a particular hypothesis when there's a violation of assumption. Because I told you the other time, assumptions need to, if I really want to know how good is a model, okay, we need to be able to investigate assumption. Let me just say what I'm actually going to present is what I did in my PhD work that I defended in 2016. And of course, in 2015, I actually got a grant to present the same work at the University of Oxford in the United Kingdom, which I did in 2015. Of course, that was what I did for my PhD. I actually developed a new approach that worked. When you are trying to compare means in more than 2 population, of course, you guys have heard about F-test, ANOVA test, but by Ronald Fisher, 1925, when assumptions are violated, you cannot trust the result from the test. Then what are we going to do? there have been several researchers that have been working on that. They, even though they improve on the quality, they trying to, contributed to the research world, but they still have situations whereby the type 1 error is exceeded, because in whatever test, when you set it's a probability of type 1 error, maybe like 5%. If it is exceeded, there's a problem. So what I did was to actually fault their work. And of course, I know one of you in this class, by the time you actually in the future, you're also going to fault my work. We live in a world where we continue to improve on what has been, and no matter how we improve on the model, even though we try to minimize the error, but the error can never be zero. Does that make sense? So which means we're actually going to continue to make an improvement. Okay, like I said, I'm going to send, detail, information about that. It's another weekend. Make sure you all stay safe and have a lovely day. Bye for now, everyone.